We've seen that the ancient Greeks defined conic sections in terms of some foci and either sums or differences of distances. They actually defined a few other types of curves that are related to conic sections that are pretty easy to write down in polar coordinates. So let's have a look at those curves. So this is the definition that they used. So first you choose a point F, which I'll put right here, and a line, which I'll call L. So I'll put L over here, and some positive number called E. And what you do is consider the collection of all of the points so that the ratio of the distance from P to F to the distance from P to L, so it's this distance divided by that distance, is equal to your real number E. It's a little easier to see what this definition is saying if we sort of write it out. So the ratio of the distance from P to F, so there's some collection of points that we're describing, and the distance from P to our fixed point F divided by the distance from P, our variable point P, to the line L. This ratio is supposed to be E. Okay, and in general there will be lots of points that satisfy this equation, and the curve is made up of all of those points. So just to get an idea of what this might look like, if E is less than 1, that means the numerator in this ratio is smaller than the denominator, and that means our points are closer to F than they are to the line L. So right in between F and L, there's going to be 1 point. So this is if E is less than 1. And as we move up and down, we kind of have to stay closer to the focus than to L because the numerator here is smaller than the denominator. So whatever curve this is, it's going to somehow swing off in this direction to the left, closer to the focus. On the other hand, if E is bigger than 1, if E is bigger than 1, then that means that the numerator in this fraction is bigger than the denominator, and so the point is further from F than it is from L, and so that's going to be something like this blue point. And as we move up and down, we have to stay closer to the line than to the point F, so something like this. Okay, so that's sort of the general idea of what these curves are going to look like, but it's, just given this equation, it's a little hard to understand or to visualize what happens to these curves as we move further up and down, exactly what happens out in these regions above and below. So maybe what we should do is put a coordinate system on this whole thing and see what happens when we write an equation in coordinates for this collection of points. So since we're talking about distances from a fixed point to some variable point P, it's actually easiest to use polar coordinates, or at least polar coordinates gives us one easy way of setting this all up. So here I'll put the origin of our polar coordinate system at the point F, just for convenience, since F is a fixed point in this setup. And the point P, our variable point, that is going to be r comma theta. All right. And so this distance here is r, and this angle in here is theta. So let's, using this coordinate system, let's write down these distances. And actually, before we do that, let's clear this denominator just so that we don't have a big fraction. So our equation is the distance from P to F is equal to E times the distance from P to L. Okay, now in this coordinate system, the distance from P to F, well, that's just r. Okay, now let's figure out, so that's equal to E times, and now let's figure out the distance from P to L. Well, that's this straight line distance directly to the right. And I guess to describe that distance, maybe what we should do is take the distance from F to L, let's call that distance D, and then subtract off this horizontal distance from F to P. If we subtract those two, the remaining piece here is the green distance we want, the horizontal distance from P to L. So we have this distance D, which, again, D is the distance from F to L. And that's a constant for this whole setup. That doesn't change. The only thing that is changing this whole setup is P as you move around on the collection of points. So we take this red distance D and then subtract this horizontal distance blue, which is, it's really just the x-coordinate of P. And the x-coordinate of P in polar coordinates is r cosine theta. Okay, so here is a polar equation for the collection of points satisfied by the collection of points that satisfies this equation. But again, still, it's nice to have this, but it's not totally clear what sort of collection of points this would give us. It doesn't really help us immediately understand what shape this collection of points would have. And there are a couple of ways we could attack the problem of understanding what this is telling us. One way to attack this problem is to solve this equation for r. If we can solve this equation for r, then we'll have r equals a function of theta, and we could just do a polar graph of the resulting equation and see what that shape looks like. So let's solve this for r. To solve this for r, we're going to have to get these two occurrences of r, here and here, on the same side of the equation. So we're going to have to start by distributing that e. We get r equals e times d minus e times r cosine theta. And then move this part with r to the left, and we get r minus plus, er cosine theta equals ed. And then on the left-hand side, we can factor out this r times 1 plus e cosine theta equals ed. And then finally divide to get r by itself. We get r equals ed over 1 plus e cosine theta. Okay, so here's a polar equation that would be straightforward to draw a graph of because it's written in the form r equals some function of theta. Remember, e and d are constants that we choose at the very beginning when we choose our constant e and the distance between f and the line. But before we graph this, I want to save the graph for later. So this is one way that we could understand the shape of the collection of points that we get. Another way is to go back to our original polar equation and see if we can write this in rectangular coordinates. So in rectangular coordinates, well, we have this r by itself, and having r by itself is kind of inconvenient when you're switching to rectangular coordinates, but having an r squared is pretty convenient. So why don't we square both sides of this equation, just so that this r on the left becomes squared. This would give us r squared equals e squared times d minus r cosine theta squared. Now the r squared on the left, that's x squared plus y squared, if we want to use rectangular coordinates, equals e squared times d minus, and r cosine theta in rectangular coordinates, that's just x. So that's squared. All right. Well, this is starting to look kind of suspicious. There are some x squareds, some y squareds, And if we multiply out the squaring on the right-hand side, there's just going to be more x's and y's. It's almost as if this equation, where we have a ratio of distances equals a constant, it's almost as if it's turning into a conic section. Well, let's see what conic section this would be. Let's multiply out the squaring on the right-hand side. So x squared plus y squared equals e squared times, so now we have to multiply this out, d squared minus 2dx plus x squared. Okay, now we need to distribute. We're going to, if this does turn into a conic section, we're going to have to combine these x squared terms. So we need to start by distributing this e squared so that we can get our x squareds together. So on the left-hand side, x squared plus y squared equals e squared d squared minus 2de squared x plus e squared x squared. Okay, now we can move the terms that have x in them to the left-hand side. We get, let's see, there's the x squared that we had to begin with, minus e squared x squared, plus 2 times d times e squared x, plus y squared. So that's everything on the left-hand side. And then on the right-hand side, the only thing that's left over is e squared d squared. Okay. Now, right here, these first two terms on the left both have x squared, so why don't we factor out that x squared? We get 1 minus e squared times x squared plus 2d e squared x plus y squared equals e squared d squared. Okay. Now, when we have a squared term for a variable and a first power term, to see what conic section this corresponds to, we would need to complete the square here. So this is going to get bad before it gets better, for sure, because we have to complete the square when the leading coefficient isn't 1. So remember, the trick to it is factor out that leading coefficient, so we get 1 minus e squared times x squared plus 2de squared over 1 minus e squared times x. So that's, I factored out the leading coefficient from my x terms, plus y squared equals e squared d squared. All right, and then the completing the square trick is you take your linear coefficient, 2d e squared over 1 minus e squared. You divide that by 2, that's just going to cancel that 2, and then square that. So we get d squared e to the 4th over 1 minus e squared squared. Okay, so this is the missing part of the square, and we need to make this missing part of the square appear inside these brackets right there where I've marked in blue. Okay, so that's 1 minus e squared times x squared plus 2de squared over 1 minus e squared times x. Okay, and now we need to make the missing part of the square appear. So plus d squared e to the 4th over 1 minus e squared squared. And then the price for making that appear is that we also have to subtract it. So minus d squared e to the 4th over 1 minus e squared squared plus y squared equals e squared d squared. Okay, now if we've done our completing the square right, these first three terms inside the brackets ought to be a perfect square. So 1 minus e squared times, so this should be the square of x plus de squared over 1 minus e squared, all squared. Okay, so take a second to multiply this squaring back out and just check that you do get these three terms I've marked in red here. So all of that minus d squared e to the fourth over 1 minus e squared squared plus y squared equals e squared d squared. Okay, so now we've completed the square. Now probably, right, we want to get our constant terms, these two terms, on the same side. So we're going to have to distribute this 1 minus e squared. So we get 1 minus e squared times x plus de squared over 1 minus e squared squared minus, and now distribute the 1 minus e squared to this constant term, but that just cancels a factor of 1 minus e squared. So minus d squared e to the fourth over 1 minus e squared plus y squared equals e squared d squared. Okay, it's starting to look more and more like a conic section as we do this. Let's move this constant term to the right. 1 minus e squared times x plus de squared over 1 minus e squared, all squared, plus y squared equals e squared d squared plus d squared e to the fourth over 1 minus e squared. Okay, it seems like on the right-hand side, maybe it would be a good idea to put this all over a common denominator. So we get, let's see, e squared d squared times 1 minus e squared over 1 minus e squared plus d squared e to the fourth over 1 minus e squared. All right, so putting these together and also multiplying out the stuff in this numerator, we get e squared d squared, that's this piece, minus d squared e to the fourth plus d squared e to the fourth. So these cancel, and our denominator is 1 minus e squared. Okay, so now using this to rewrite our equation, we get 1 minus e squared times x plus de squared over 1 minus e squared squared plus y squared equals e squared d squared over 1 minus e squared. Okay, now this almost looks like the equation of a conic. The only thing is, right, we're used to having a term with x squared and a term with y squared, but we're also used to having a 1 on the right-hand side instead of this crazy fraction. So let's just multiply both sides of this equation by whatever we need to make the right-hand side 1. And that would be 1 minus e squared over e squared d squared. Okay, so on the right-hand side, we're going to get 1. We have to do this on the left-hand side as well. 1 minus e squared over e squared d squared. Okay, on the left-hand side, we need to distribute this thing we're multiplying by. So we get 1 minus e squared squared over e squared d squared times x plus dE squared over 1 minus E squared squared plus, and then distribute this thing over to our y term as well, 1 minus E squared over E squared D squared times y squared. Okay, so now we're really close to having this look like a conic section equation that we're used to. All we need to do is write it so that the x squared part and the y squared part are in numerators, and these pieces that have all of these constants in them are in the denominators. So that would give us, right, you can always make that happen just by replacing this, by putting this in the denominator, but replace it with its reciprocal. So we get x plus dE squared over 1 minus E squared squared over E squared D squared over 1 minus E squared squared plus y squared over E squared D squared over 1 minus E squared equals 1. Okay, so we finally have a conic section. So let's figure out what conic section this is by identifying various pieces. So one thing to be careful about is, because there's a plus in the middle here, it looks like this is going to be an ellipse. And it might be an ellipse, but if you look at this denominator underneath our y squared, this 1 minus E squared part could be positive or negative, right? It depends on E. If E is small, then 1 minus E squared is positive. If E is large, 1 minus E squared is negative, and that would make this sign in the middle here be a minus sign in principle, and so we wouldn't get an ellipse, we'd get a hyperbola. So have to be a little careful about that. But still, we can identify all of the pieces of the equation of a conic section. So first, let's look at the center. So there's no shift in the y direction for this conic section. So the y coordinate of the center is at 0. And the x coordinate of the center, it looks like we have a shift to the left here. So the x coordinate is the negative of, right, this stuff here. So negative dE squared over 1 minus E squared. Or if we wanted to absorb that minus sign into the fraction, we could write dE squared over E squared minus 1, comma 0. So there's the center. Some people call the x-coordinate of the center h, and so h is dE squared over E squared minus 1. Okay, also a squared is, right, the stuff underneath our x term squared, so E squared D squared over 1 minus E squared squared, and B squared, that's the stuff under y, that's E squared D squared over 1 minus E squared. Okay, now assuming that this whole mess gives us an ellipse, and remember we get an ellipse when E is less than 1, if we have an ellipse, then a squared is equal to b squared plus c squared. And remember, c is the focal radius of the ellipse. Now we know a squared and b squared, so we can find c squared. So c squared is a squared minus b squared, and that is E squared D squared over 1 minus E squared squared minus E squared D squared over 1 minus E squared. Probably we should put these over a common denominator, so let's multiply this one by 1 minus e squared. We get e squared d squared over 1 minus e squared squared minus, so our new denominator over here is 1 minus e squared squared, and in the numerator I'm going to distribute this stuff. We get e squared d squared minus d squared e to the fourth. Okay, and then now we can do this subtraction. So our denominator is 1 minus e squared squared. And then in the numerator, it looks like these e squared d squareds are going to cancel, and we're going to get d squared e to the fourth. Okay. But wait a second. This looks familiar. If you look up at the center of this thing, it's de squared over e squared minus 1. So what we got for c squared is just the square of the center of the ellipse. So what this is saying is, right, we had our origin of our coordinate system, right, and our polar axis. The center of the ellipse was out here somewhere, and so an unshifted ellipse has its center at the origin, but our ellipse has been shifted over to here, but also the focal radius is equal to this shift, it looks like, right? So since c squared is equal to h squared, that means c is equal to h. And so the center gets shifted to the right by this amount, but also the focal radius means that the focus is c units to the left, but that's back at the origin. So the origin in this whole setup, remember, was f, and it turns out that is the focus of the ellipse that we get, or a focus of the ellipse. Okay. And actually, I think the way I have this set up, I need a minus sign just to make c positive. So the center is actually going to be over here. So the shift is that way, and the focal radius is there. And remember, our vertical line is over here somewhere, and our ellipse is like this. And so this was when e is less than 1. All right, so it turns out that this crazy equation that we started with, this idea of, way up here, this idea of having a ratio of distances, so choosing a focus and a directrix, essentially, and having a ratio of distances be constant, after all of this terrible, terrible algebra, it turns out that we just get a conic section. So all of these equations that we started with, r equals ed over 1 plus e cosine theta, these are all conic sections. So when I said they're related to conic sections, well, they aren't just related conic sections, they are conic sections. And we've seen when e is less than 1, you get an ellipse. If e is greater than 1, then it turns out you get a hyperbola. Okay, the algebra for the hyperbola works out pretty much the same. It's just you have a minus sign in front of your y squared term. When e is equal to 1, the algebra works out a little differently. Some of the algebra that we did actually assumed that e was not 1. But if you go back and see what changes when e is equal to 1, I'll give you a hint, the x squared terms cancel. And so you end up with a conic section where y has some squares, but x doesn't. And that gives you a parabola. All right. And just as sort of a final parting shot, if you write down A and C, it turns out that this number E is equal to C over A. But in the case of the ellipse, we already had a name for this quantity. It was called the eccentricity. And for an ellipse, it was always between 0 and 1. And you might have wondered when we talked about ellipses, well, what happens if the eccentricity gets equal to 1 or bigger than 1? Well, it turns out that those give you parabolas and hyperbolas.